Welcome to our presentation on quality inspection using casting product images with machine learning. Firstly, some background. Manufacturing is the basic process to obtain a product from raw materials. For a product to be usable and of high functioning quality, it needs to pass quality control, which ensures that products are free from defects and are able to perform the intended purpose successfully. We focus on casting, which is one of the many manufacturing processes. Casting involves pouring molten metal liquid into molds to achieve a desired shape. This process sometimes faces defects such as shrinkages and holes, which need to be identified and removed to ensure that the performance of the final product is not affected. Traditionally, quality control of casting is done manually. This is time-consuming and subjected to human error. Furthermore, delivered product could be rejected by customer, resulting in loss of money and trust. Hence, our objective is to identify a machine learning model to distinguish casting products which fail quality inspection.
Moving on, I will briefly introduce casting process and visual inspection. There are many different methods of casting, such as gravity die casting and pressure die casting, while the most common method is sand casting, and the materials of the casting mold can be sand, wood, ceramics, etc., while most of the materials to be cast are metals. There are 5 main steps involved in the casting process. The first step is to select the shape of the mold and prepare the materials to use, as mentioned in the previous slide. The second step is core making, which is optional and only required if the casting has internal features such as hole. The third step is mold making, which is to create different types of molds using the materials prepared in the first step. And now comes the most important step, which is pouring, where metal is melted and poured into the mold. And lastly, once the melted metal is cooled and solidified, the casting product is removed from the mold and cleaned. The defect detection plays an important role in casting manufacturing. Most traditional methods of defect detection are based on manual inspection, which usually involves high labor costs, low efficiency, and low accuracy. On the other hand, machine learning-based inspection is getting more attention from manufacturers who are looking to reduce costs and increase efficiency. It also ensures uniform and objective testing standards and high accuracy and stability. Through literature review, we have found that machine learning-based method enables early detection of defects and hence increases defect detection by 90% and productivity by 50%. It is also easily accessible and available for business to develop and implement, and therefore applied in many industries where potential cost of error is high.
Hi, I'm going to talk about business problem. First, ineffectiveness. Casting defect is the main reason leading to low performance, short service life, and failure of castings. At the simplest level, they manifest as rework costs or casting scrap costs, but in many cases, the resultant costs may sometimes be passed on to the foundry by their customer. And besides, foundry personnel may not have the time to prevent occurrence of these defects. Second, high inaccuracy of manual inspection. According to research, visual inspection errors typically range from 20% to 30%. Visual inspection errors in manufacturing take one of the 2 forms: missing an existing defect or incorrectly identifying a defect that does not exist. Misses tend to occur much more frequently than false alarms. Third, high cost. We capture, segregate, and track the costs of the casting defects in 4 areas. Failure costs are those associated with correcting non-conforming material. Appraisal costs are those related to detection of defects. Preventive costs are those associated with activities assigned to prevent defects. And manual inspection remains a costly venture due to the appointment of trained individuals. Last, about defect rate and profit. One major problem is with casting defects, where it's estimated that for every 1,000 tons of castings, 75 tons are defects that need to be milled down again, which creates severe issue for the foundries.
In my part, I'm going to talk about the data, the methods, and the results. The data consists of 7,348 casting manufacturing product images. These photos are all top view of submersible pump impeller. The table is an overview of the dataset. Below are the example images of products with different types of defects, including blowholes, burr, turning material defects, etc. When we zoom up on some specific parts of the pictures, we can see some differences between defective and non-defective products. When we compare the details, we can find that defective and intact areas have visible differences in colors, lines, brightness, etc. We choose orange for data processing and model training, as it allows us to focus on exploring data analysis instead of coding. Image embedding reads images and uploads them to a remote server or evaluate them locally. Deep learning models are used to calculate a feature vector for each image. Here are the embedding models that Orange provides and that we applied to our research. We choose 5 classical and popular machine learning models in our research, which are logistic regression, G-boosting, decision tree, random forest, and neural network. After trying all the 6 embedding models, we choose Inception v3 as it enables highest accuracy in the subsequent performance of machine learning. Based on the results we get from Orange, we decide to apply neural network as our machine learning model, which has a higher classification accuracy, a better receiver operating curve, and a relatively more stable performance in the future application.
Next is business implication and recommendation. The benefit of implementing AI can be translated into 2 major aspects, which are operational and financial implications to the company. As we can see, machine learning can reduce inspection time up to 49.8% and further eliminate bottlenecks. Hence, it can increase process efficiency. On top of that, our team has developed machine learning with 99.7% accuracy, which is higher than human vision. Therefore, this can increase inspection accuracy, reliability, and consistency. Furthermore, for new product, machine learning will only need training in early stage and can be utilized in long term. Hence, it has high scalability. These operational benefits can be translated as financial implications. With higher process efficiency, we can reduce production and opportunity costs, we can increase production rate and capacity, which will increase revenue. With higher inspection accuracy, reliability, and consistency, we can reduce unnecessary costs of rework and disposal, external failure costs, and increase customer trust. Furthermore, we can also decrease labor and training costs. Therefore, utilizing machine learning in inspection leads to higher profitability. Next is recommendation for implementation. This project recommends on implementing AI visual inspection on the final inspection, which is inspection 3. And we recommend using optical system to capture casting product. The devices needed are camera, box and tune illumination source for stable lighting condition, CPU or GPU, light alert, and software. There are other implementation opportunities for AI visual inspection, such as root cause analysis, predictive maintenance, and production optimization. Here, we can also see its implementation opportunities in other industries.
Next, limitation. Our model currently identifies external defects. However, we do know that internal defects such as density issues and holes could happen. Second, our model is unable to determine the functionality of the casting products. Functionality is affected by various other factors, one of which is dimension error. In conclusion, we have successfully developed a neural network model to perform quality control of casting products with 99.7% accuracy. This has operational implications such as reduction in inspection time, increase in inspection accuracy, and higher scalability. Furthermore, financial implications include increase in production rate and decrease in production costs, which lead to higher revenue, lower overall costs, and higher profit. Furthermore, the model is easily implementable using our proposed implementation plan. In the future, we could consider utilization of 3D vision sensors to not only detect surface defects, but also detect structural, dimensional, and density defects of casting products. Thank you for your attention.